So I'm going to be going over today first a brief overview of just who GTI is, and then a speed through some of the methane related work that GTI does kind of across the natural gas value chain. And then my particular area of interest and area of work has been in the end use sector. So I'll dive a little bit deeper into two projects that I worked on in that area. So Gas Technology is an independent, not-for-profit research organization that does research and approaches a lot of the tough energy challenges that we're facing, especially in the natural gas area. And our expertise really covers the whole natural gas value chain, so downhole to the burner tip, including different energy conversion technologies. Our main campus is at Des Plaines in Illinois, where we have most of our large lab space, including a full-size gasifier. So there's a lot of cool stuff going on there. In the supply and conversion areas, we do a lot of unconventional gas resource characterization, conversion technologies, gas processing and analytical services, along with a lot of methane emission quantification. And on the delivery and utilization end, a lot of work in the delivery sector around safety, environmental and emissions, in the residential, commercial, and industrial, high efficiency, next generation equipment research, building systems, and then in transportation, natural gas and fuel cell vehicles, and research in low carbon fuels. So I'm going to jump now into really a speed through. I realized after I talked with Evan that I have way too many slides to go through. So this is going to be fast on the overview side and then a little bit, slow down a little bit on the deep dive. I don't think I need to go over this slide for all you folks. You're all in this area. You know the importance of quantifying, understanding, and finding ways to mitigate methane emissions. I think the only thing I want to emphasize here is the importance of working across all segments, upstream, midstream, downstream, and also alternative low carbon fuels. So for GTI itself, the methane emission work that we're doing, again, covers the whole value chain for natural gas and can kind of roughly be binned into three categories of technology development, so sensors, detectors, drones, characterization and development, and then second, data gathering, emissions characterization and analytics or models, and finally, mitigation solutions. So this kind of lists a lot of the different funders and folks that we're involved with in those areas. Two that I want to highlight quickly are OTD. This is the Operations Technology Development. It's a collaboration, a not-for-profit corporation that's led by 26 natural gas utility members that serve about 50 million natural gas customers in the US and Canada altogether. And they work together and fund a lot of research developing advanced technologies focused on the distribution system. So a lot of the work that we do on methane characterization and mitigation in distribution is funded by OTD. For downstream, we have done a lot of work with CEC, and I will go over one of those projects today, as well as CARB, and then also UTD, which is the Utilization Technology Development. And this is a not-for-profit collaboration partnership of 20 natural gas distribution companies, and they conduct near-term applied research in energy efficiency, environmentally friendly end-use technologies, and then also funded the research I'll be talking about on tankless water heater emissions. I wanted to do just a quick overview of Collaboratory to Advance Methane Science, which is an industry-led research collaborative that GTI is helping to oversee and guide. And they have a number of projects on the upstream side, really helping to develop models and measurement techniques for methane emissions in oil and gas fields. So some really neat work here. Definitely for any of these that I'm kind of just running through, if there is a lot of interest in hearing more details, feel free to reach out to me or reach out to Evan, and if it makes sense for someone to come and talk talk through it in more detail later. I'm sure that they would be happy to do that. Another area in upstream mitigation, compressor, helping to redesign, develop new types of compressors and leak mitigation around pneumatic devices. For those of you familiar, well, all of you familiar with the greenhouse gas inventory, this is a big source of methane emissions in the transmission and distribution sector. And so a lot of work going into designing this linear motor compressor technology that helps to capture and recover natural gas that's leaked from compressors. We also do a lot of work in the development and evaluation of methane detection technologies. So we actually, out at our Des Plaines campus, have a little kind of miniature pipe field that we can go out and do evaluations there, looking at different point and shoot methane sensors, evaluation of stationary continuous methane sensors or monitoring systems, and then also different remote sensing or drone-based sensors. On the distribution side, some neat work here directly with different LDCs, helping to both help them understand more the emissions from their distribution systems, and also methods for prioritizing leak repairs in order to most effectively use their time and resources to mitigate emissions. So this was all, that was all on the distribution and upstream side. I'm gonna move now to end use methane emissions. And this kind of summarizes a number of the projects that are ongoing in different spaces. So we have research going on with EPRI measuring methane emissions from industrial facilities, with DOE measuring emissions from industrial customer meters, work in the commercial sector and the residential sector that I'll talk about in a little more detail, and then also residential customer meters. So this is kind of a plug for Chris Moore, one of my colleagues, was going to come and talk a little bit more about the commercial industrial meter leaks that he led this project, developing new emission factors for industrial meters. And unfortunately, he wasn't able to make it today, but they did some really neat work here that enabled them to develop regional emission factors that are more representative of the industrial meter sets that are present in different meters or in different regions of the US. And results indicated emission factors that might be 6 to 8 times higher than what's in current inventories. But if folks are interested in that, I'm sure that he would be happy to come another time. All right, as I transition into some more details of end use projects, I wanted to kind of put it into the big picture for GTI. Why is GTI interested in doing methane emission research in the residential and commercial sectors? And it really comes down to our goal of helping to reduce greenhouse gas emissions from the built environment, and the role that natural gas and also renewable natural gas can play in that. And so within our spectrum of research that's going on, a lot of it is focusing on energy efficiency for near-term reductions, next generation equipment with COPs of over 1 for kind of continued efficiencies, alternative low carbon fuels, and then also lower methane emissions. And so methane emission quantification and reduction fits into this broader goal that we're working on. All right, hopefully that wasn't too fast, but we'll go now into a deep dive into 2 of the projects that I particularly was involved in. And I'm happy to talk about these 2 particular end use projects. One was measuring in the field commercial food service methane emissions in California restaurants. And then the second was lab measurements of methane emissions from tankless water heaters. And I think that talking about both of these helps to emphasize the importance of both the field measurements and the lab measurements and understanding different factors that contribute to methane emissions. As I go through it, you'll kind of see some of the really high emitters that we are seeing out in the field had a lot more to do with maintenance issues and those sorts of factors. Whereas in the lab, we could focus a little bit more on the actual design of the equipment, and you have a properly operating piece of equipment, but where are the emissions generated in that event? And also, please feel free, jump in with questions as I'm going through these. I hope that it can be a little more of a discussion instead of me just talking at all of you. So actually, before I jump into this, I'll just kind of pause and see if anyone wants to jump in with anything right now. All right.
I think this would be a different talk, but that basin level methane emission estimation tool sounds like something I'd love to hear more about.
Yeah, just definitely just shoot me an email, and that will remind me to reach out to the project manager for that, and we can see if that'll be, if she could come and talk more about that. It is a really neat tool. So I don't have enough knowledge of it. I'm not involved in that project enough to go into any more details now, but.
I have a quick question actually around the various detection technologies that you guys were testing out, right? You had like some of those handheld ones and some of the mid-wave infrared ones and the drone mounted. Any favorites?
Oh, that's a great question. So we have a really neat, I took the slide out, but we have a really neat kind of matrix that talks about, that lays out when is each one of them useful. So it's kind of it depends on what your goal is question. So let me see, Olya, if I can go ahead and share that slide with you, and hopefully that'll be helpful. And if you have any kind of specific goals that you're looking for in the detection, kind of the detection technology, then I can tailor it a little more towards that too.
Yeah, sounds great. Yeah, I'm happy to follow up offline. Thank you.
Okay. All right, I'm going to jump now into fugitive methane emissions from natural gas systems, specifically commercial buildings, and even more specifically, commercial food service in California. This was a California Energy Commission funded project, and it was a very a small level field study. So really the goal of it was to develop more of a methodological framework, and as part of that, conducting some surveys. So we ended up going to about 20 restaurants in order to validate the framework that we had developed for quantifying methane emissions. And I do want to also recognize LB&L at this point. Specifically, Mark Fisher was really a great partner in developing the methodology that we ended up using for this effort. So measurement objectives, as we're doing the development of the methodology, was we wanted it to be a rapid but also sensitive quantification of methane. Needed to have different methods for both point leaks as well as emissions from incomplete gas combustion, since the goal was really to understand the whole building emissions. And this was definitely more of a bottom-up approach, as you'll see later as I go through the methodology in a little more detail. So we ended up using two pretty industry standard instruments, a Bacharach high flow sampler, and then also the Los Gatos, I guess now it's actually ABB, but their ultra portable greenhouse gas analyzer that measures methane and CO2 at a really fine resolution. So for point leaks, for some of you, this is a fairly standard way of measuring point leaks in industry. So you gather them into the much larger flow of diluting air from the high flow sampler, and then are computing the leak rate by mass balance, comparing the ambient concentrations of methane and the concentration of methane in that collected stream with a known flow rate. So for our specific effort though, we ended up pairing the high flow, which is really more for larger natural gas facilities and larger leak rates, with the UGGA that could measure these really tiny fugitive methane emissions and leaks that we were finding in the piping inside of buildings. For the exhaust, here we are just using the ultra portable greenhouse gas analyzer and looking at the the relative enhancement of methane and CO2 that we measured in the exhaust. So we take an ambient measurement and then probe the exhaust, and that relative enhancement of methane and CO2 enabled us to get a ratio that could be used to calculate the fractional methane emissions from combustion. And that was really just based off the fact that if you have a mole of methane coming in, if it combusts 100%, you'd have the same number of moles of CO2 coming out. And so by looking at how much methane we were actually seeing in that exhaust stream corrected for just the ambient concentrations, enabled us to get a pretty good sense of what the fractional fractional combustion efficiency was. So as I mentioned, we ended up going to about 20 restaurants, and I will actually just skip through this for the sake of time. So 20 restaurants, ended up sampling about over 2,000 different piping components. So that's how many we actually went through and touched with. We're using a Sensit to look for leaks at each of the components. So ended up sampling about 2,000 of those and about 180, taking measurements of about 180 appliances. This is just showing the methodology. So sampling each of the joints with the Sensit, and then when we got a hit, actually measuring it with the high flow. For the equipment exhaust, probing in the exhaust and measuring those methane and CO2 enhancements. So this is what raw data would look like for a leak measurement. You have the ambient, you start collecting the leak, measuring the methane enhancement there, and those difference multiplied by the flow rate is going to get you your leak rate. For exhaust measurements, what we're looking for is a correlation between the CO2 increase when you stick your probe into the exhaust and the methane increase. So when you have incomplete combustion, you're going to end up basically with this positive linear relationship between the methane and the CO2. When you have complete combustion or possibly even some methane scavenging, then you're going to see the opposite. And the ease of this methodology was great for getting in and out of restaurants. I'm not sure if any of you have worked in food service in former lives, but it's a really busy. You'd have to get in there, in the hour before they started prepping, do everything we could, and then get out. So one of the downsides, though, is this whole study was all based off of steady state measurements. And so as you'll see in the next talk, or many of you who do, say, maybe residential equipment, methane emissions, a lot of the emissions are coming from that cycling behavior and from the ignition and extinction. So that's definitely a gap in the study that we'd love to get back out there and do some of the transient emissions. But just for your context, as you're looking at results and such, this was all steady state. So we looked at the fraction of unburned methane as the fundamental metric because it's easier to apply to as we try to expand it over populations and different types of equipments, and just gives a lot more flexibility as we did some of the statistics at the end. This is a histogram of the exhaust emission measurements and fraction of unburned methane from the appliances. So you see we've got majority that are operating well, 0 emissions, and then you have this really long tail distribution. And I just gave 2 examples of ones because you look at these fractions, how can it be 0.3 for methane? That seems so high. But you looked at some of the equipment that was out there and the disrepair that it was in, there's methane coming from all these ports not being combusted because there's something that's blocking the ignition from going all the way around the burner. So as you get into some of these places where maybe maintenance hasn't been kept up, then you are going to see really, really high emissions. Again, this just kind of shows the range of equipment that we measured and the variation in emissions that we saw. The fraction unburned is on the y-axis. For pipe leaks, really what I want to focus on here is that the majority of what we measured, there was not leaking. Only about 1.5% of the components that we surveyed had measurable emissions. And of those that had measurable emissions, the top 3% or so were causing over 50% of the total emissions that we measured. And just to keep time down, this is showing, this is all the different restaurants that we visited. Front is pipe leaks. Middle is the emissions from exhaust, and then total in the back. So it kind of shows the range of what we're seeing. And generally when we're seeing these really, really high emissions, that might just be from one or two pieces of equipment that had maintenance issues, or a quick connect or some other piping component that really needed to be replaced. So this is more to give a sense of, okay, well, we did all these field measurements. What really was the goal of this project, though, was to see how it could be applied to larger estimates of larger populations of restaurants. So the data from the field data collection and the statistical analysis was used to create different probability distributions of the fraction of unburnt methane for appliance types, or probability distributions of the mass emission rates from the pipe components. And then from these distributions, a large theoretical population of appliances and piping components was created. And that statistically generated population was the sampling pool that then we used for the different scenario analysis. So for each scenario, we had to basically create an inventory of appliances and piping components. And so a pretty good knowledge of the population that you're looking at is needed to use the data. This is just an example of the output. So understanding, okay, what are the different types of restaurants? What is the population of appliances? Because each appliance has a different emission profile for each of those restaurants, and then doing the Monte Carlo simulation to get the output and total emissions. And I just want to, because we'll care about this number later, this was a scenario that we ran for kind of a fake large region that had about 24,000 restaurants. So you could think of it as probably about the size of kind of like the LA area, San Diego, LA plus San Diego area, pretty big region. And so from our measurements, we were getting about 0.16 million tons of CO2 equivalents per year. So we'll just focus on, this was the different 7 scenarios we ran, but again, we'll just focus on that first one. So what are the main findings? So first, from this, again, this was a very small scale field measurement, so really a bigger sample size would be ideal if you're going to be using this methodology to extrapolate to, say, the state or larger regions. But from the small scale field measurements, the results did indicate that the fugitive emissions from commercial buildings might be higher than characterized in the current inventories. So again, this is the California Air Resources Board methane inventory. For the whole commercial sector, the methane emissions were estimated at 0.02 million tons of CO2 equivalent. And then from that kind of scenario we did that might just be representative of a portion of California, we were seeing more like about 2 orders of magnitude, or an order of magnitude larger than that. So that was the first finding. And then next, though, that for both the pipe leaks and also the appliances, the top 3% of the leakers accounted for over 50% of the total fugitive emissions. And so there's a lot of potential here for identifying and mitigating those small portions for a really big impact on reducing emissions. All right, I'm going to do another pause here and just see if there's any questions or discussion that people want to bring up, or we can save it to the end as well.
I wonder how's the accessibility to the restaurant for the actual measurement? How easy?
So are you talking about getting permission to go in, or once we're in, kind of getting access to the equipment?
Or in both?
It was very challenging. It was very challenging. That's part of the reason the sample size was so low, is just getting permission from the restaurant owners. We actually found it was a lot easier to reach out to independent restaurant owners and just talk directly to the person who owns the restaurant. Usually they were a lot more flexible. Once you start getting into, say, restaurant groups, and then you have to start calling up to whatever corporate headquarters there are, I don't know if we got into any restaurant group restaurants. Those were really challenging. And then definitely working around their schedule. So I had a few where I was in there at like 3 in the morning because they start at 6. And if you want to measure all of the equipment, you're going to be there for 3 hours. So
Well,
Restaurants were difficult just because of their schedule, hours of operation. You cannot be in there when they're just starting prep. And then also just the bureaucracy once you start getting to the larger restaurant groups, that they're not too interested in messing up their operations in any way.
So I imagine for a lot of these bigger restaurant companies, were one of their major concerns, like whether or not this data would affect their business, like specifically, or whether or not like your results of like say Red Lobster would come back and show everyone that Red Lobster has really bad emissions or something.
Yeah, and even though definitely everyone was assured their data is going to be kept private, but you're right still when they're thinking about, well, what's the overall impact on the restaurant industry and how we're perceived, would definitely be a concern.
So a few things. This is really cool. Yeah, and then this is so good. I mean, it's remarkable how consistent the basic findings of methane field surveys are, sort of regardless of what they're looking at.
Yeah, it really is.
And yeah, I mean, like 3%, 50%, like 550 rule, that's almost everywhere. And so I guess a few questions I have. One is, did you compute a fractional loss rate? So it looks like the numbers are much higher than the CARB estimates. And I'm wondering, are the CARB estimates, is that a fractional loss rate of like 0.1% or, so how does this fit? Yeah.
I did not do that, Evan. That's a great question. Make me want to try and start doing that math right now, but I don't have the answer for you off the top of my head.
Cool. All good. Yeah. And I guess the other question is along the lines of when doing oil and gas field surveys, especially anything that involves on the ground, getting permission for anything like that, then you end up with the volunteer bias. And having looked at basin-wide data from New Mexico in particular, it's totally clear that there are some operators that have much better emissions profiles than others. And yeah, so that raises a big question about it. For restaurants, it seems like it would be difficult to get basically the way that for on the ground field surveys in oil and gas, the only case I've heard of that didn't have this volunteer bias issue was Arvind Ravikumar, who's now at Harrisburg University, basically getting deputized by the Alberta government to go wherever he wanted and take methane measurements. I don't know if CARB has that kind of authority for restaurants, but
no. So that's a really good point. And part of the problem we have is just one, our sample size is so small. I mean, we're talking about 20 restaurants and there's tens of thousands of restaurants in California. So I think that that's one issue or one challenge that we had. In terms of the kind of volunteer bias, most of the connections we made were actually through personal connections. So say, oh, I have a brother who runs 5 restaurants, things like that. Or, we actually measured a lot of restaurants around Davis where, hey, we go eat their lunch every day. They're going to be nice to us and let us come measure their restaurant. And so based off the quality, the variation in the quality of the appliances that I saw, and usually the reason for letting us in was more personal rather than, I'm not quite sure how to say this, but maybe an understanding of why we were doing what we were doing. I don't know if there was a bias towards restaurants that had lower emissions. But it's such a small sample that it's hard to say.
Mm-hmm. Yeah, I agree that probably, I mean, my guess is that if there were restaurant owners who were really self-conscious about like not wanting to look bad because of high emissions, like they would have cleaned the burners and that kind of thing.
Right. Yeah, well, it was pretty interesting to we got into a few more institutional organizations, so universities, where they have a really, really rigorous maintenance. So every year, at the end of the year, they're going to shut everything down, clean it. And so even there, though, sometimes we were seeing really high emissions for certain equipment, and then it tended to be maybe more of a pressure issue. So maybe you're blowing the flame off the burner, something like that. So it was still a maintenance issue often, but not one that was visually obvious, just a cleanliness issue. So there's a variety of things that were contributing to it.
Cool.
All right, if there's nothing else right now, I will go on to the next topic, which I think that at least a few of you on the line have heard some version of this talk before, but hopefully not too many of you. So this I'm going to jump into. It was lab measurements of tankless water heaters that we did over at our Des Plaines lab in GTI. And so the goal was to get a lab-based test of the methane emissions from a number of tankless water heaters in order to better understand different emission factors, and specifically focusing on different controlled operating modes, so we could understand how those emissions changed as we changed the operation of the water heater. And we decided to start with tankless water heaters for a number of reasons. One was a number of studies that had come out at that point surrounding the emissions from tankless water heaters. There's obviously the work that Eric was doing and had presented at different places. From the University of Illinois in Urbana-Champaign, there was a study that came out from Marin and Francisco, and then also Lawrence Berkeley in their survey of emissions from residences in California had highlighted tankless water heaters as a potential high methane emitter. And then also just their growing presence in the market and the representation as an environmentally conscious alternative because of their gas use, having an understanding of, okay, well, how does higher methane emissions or the potential for higher methane emissions impact that? So some of the things that we were thinking about in terms of how the methane emissions might be significant was the burner design. So you see a lot of different burner types, cartridge types, mesh types, and that have different kind of potential for maybe doing some quenching of the flame. Also different modulation controls as the hot water demand changes. Some are going to just have a fully modulating valve. The whole burner is going to modulate up and down across the whole operation range, whereas others have different stages that will turn on and off. And then different airflow controls as well. So in our selection of the water heaters, this is a pretty small project. We only looked at 3 water heaters in the lab, but we tried to get ones that had some of those differences that I just talked about. So the first one was a non-condensing fired unit, had a constant speed combustion air blower. So we were seeing really high excess air when it was at low firing rates. Then and it was a cartridge style, and it had 3 regions of the burner that would turn on and off to meet that demand. The next 2 were both condensing down-fired units, really tight control of the excess air with their blower, and mesh style burners. And the big difference for these was that one of them had a fully modulating valve. This is water heater number 2. The whole burner would just modulate up and down. And then for unit number 3 that we looked at, it had 2 stages of the burner that would ignite. Each one could also modulate, but they would ignite or extinguish depending on the level of demand. This is not going to be news for any of you who have done this sort of equipment measurements before, but I wanted to talk a little bit about the analysis or data collection and analysis methods that we used, and mainly the challenges that we faced. We were doing direct exhaust sampling. And so with that, you're going to run into some methane sampling challenges because of the large range that you see in the methane concentrations in the exhaust. So you might see pre-ignition or extinction puffs that are greater than 10,000 ppm of methane, down to a steady state emission that's less than a ppm, so below ambient. And then also they're highly transient. So those peak emissions at ignition are only at the peak for maybe a second or two, and then are going to be settling out within 30 seconds. So our approach for handling that was actually using a dual analyzer system. So we had both our rack-mounted flame ionization analyzer that had the range that we were looking for, and also a really short response time, measuring those concentrations to be able to capture the shape of the peak. And then also the UGGA that we used in the last study that I talked about as well. And for that, we had the PPV resolution that we wanted to really understand what those steady state emissions were when it started getting really low. Some other things, high resolution gas meter, controlling the outlet temperatures, water flows, power to the unit, exhaust temperatures, and looked at 3 different operating modes that I'll talk about in more detail later. In terms of how we actually calculated the emissions, we were using a mass balance approach that was looking at the exhaust gas mass flow rate calculated from the gas input that we were measuring, and then also the exhaust composition that was being directly measured, CO2, methane, and the other ones that you see listed up there. And that method, the mass balance method, works really well for combustion periods when the burner is on and operating steadily. Not so great for those transient periods when the burner is first igniting or right after it extinguishes. So we supplemented that also with direct exhaust flow measurement with a pitot tube in the exhaust that was used to understand what those flow patterns looked like during the transient periods. And the combination of the mass flow rate of the exhaust combined with the actual measured methane concentration got us our emission rate. So the 3 different tests that we ran, we did a baseline test, a modulation test, and then a 24-hour stimulated use test. So for the baseline test, this is just the max hot water draw that's going to meet our outlet temperature. It gave that steady state emission at a firing rate that was close to the design firing rate of the burner. And then also we got the ignition and extinction emissions from that. So this is just showing for ignition and extinction, we're looking at about 50 to 125 or so milligrams of methane for each ignition and extinction event. For the steady state, this is in grams per minute over here. Tankless water heater 2 and 3, we basically were measuring nothing or very, very low methane in the exhaust. And when you actually look at the amount of methane that's being consumed from the combustion air that's going into the water heater as well, these actually would be a net negative emissions at that point. Difference in tankless water heater number 1, where we're actually seeing a higher level of emissions during steady state operation. So that ends up being about 0.07 when you're looking at a massive methane for the massive natural gas that's introduced to the water heater. Or if you think, I thought it's useful sometimes to kind of think about also when you're getting how big are these ignition and extinction emissions compared to steady state emissions when you look at it on an equivalent basis of how many minutes of steady state operation would it take to equate to those ignition and extinction emissions. So for tankless water heater number 1, it was about 3 minutes or so. For the next 2, it starts getting, their emissions are so low, it starts getting kind of nonsensical. Pretty much everything's coming from ignition and extinction. And again, emphasizing that was for operating close to the design rate of the burner. So the next test we did was a modulation test, and this we wanted to understand how, if we already have an ongoing draw at the water heater, what if we change that draw, either cutting it or increasing it instantaneously, how does that affect things? And so that gave us both the emissions at that actual modulation point, and then also helped us understand as we kind of stepped through these different draw rates, well, what are the steady state emissions at different firing rates of the water heater? So this first, the first plot that I want to focus on, this is actually looking at any peaks of emissions that occurred at the point that the draw changed. And really the big takeaway from this is if there isn't a burner or a portion of the burner that's turning on and off, you're not going to see emissions. If there is, you are going to see emissions. So pretty much everywhere for tankless water heaters 1 and 3, which is the blue and the gray bars, they had portions of the burner that were turning on and off, and you see those emissions that are pretty similar to your ignition and extinction emissions. For tankless water heater number 2 that had the fully modulating burner, the only time that we saw emissions during those modulations was when we suddenly cut the flow rate down to 1 GPM from its highest water draw rate, and the burner briefly turned off. Just some other interesting things that occurred during the modulation testing. For tankless water heater number 3, sorry, this is a kind of messy graph, but it's showing the gas input, and then the orange is the blue, and then CO2 is the, sorry, gas input is the blue, CO2 is the orange. So you see here during these, when we had either a 1.7 or 1 GPM draw, this cycling back and forth of the CO2 concentrations in the exhaust. And what was happening was the two sides of the burner were actually rapidly igniting, turning off and igniting, and kind of switching which side was operating. So it was, when we start looking at these steady state emissions, that's where you get these outliers here, is with that burner behavior of the cycling on and off, as the outlet temperature is pretty much met and it's trying to decide whether or not to turn on the burner. But I want to zoom in, if we kind of put aside that operational issue for now and instead just look at the periods where the burner was operating steadily. For tankless water heater number 2, at the full range of rates that we looked at, we were seeing no emissions. For the other 2, there tended to be a pattern when we look at it on grams of methane per kilogram of natural gas that's being supplied to the burner, that as it gets closer to its design rate, that ratio starts to go down. The next test we did was the 24-hour simulated use test. So basically running the DOE UEF testing for the high usage case. So that's 14 draws over 24 hours for a total of 84 gallons a day. And that was to give us a sense of how much methane emissions are we looking at for a tankless water heater each day. So we ended up with about 2 to 3 grams per day of emissions for all the water heaters, and which when we're looking at that on a volume of methane per volume of natural gas is about 0.27 to 0.36%. The majority of this is coming from the ignition and extinction. In the case of tankless water heater 2, it's coming only from the ignition and extinction events. And because it is coming, the majority of it is coming from those ignition and extinction events, the grams per day or the percent emissions is really specific to the firing pattern that's assumed for the test. So I have a slide a little later that's stealing some information from Eric's report, but in his field testing, he was seeing users that were maybe having 30 plus draws per day. So you're going to see a much higher percent emission rate for that situation than this more controlled simulated use case. So summary, ignition and extinction. This is where really the emissions are happening for every water heater that we looked at. During modulation, again, it's only if there's ignition and extinction at the burner, and then steady state operation, it depends on the burner design and also the firing rate affects those. Just to put it in context, this is using 0.35% emission rate. I wanted to just put it in context of, well, what about the overall emissions from the water heater? What about overall emissions from a home? So here on the left, this orange bar is the methane emissions at the water heater that we measured. So it ends up being about 2.6% of the total CO2 equivalent emissions from the water heater, the majority of it coming from combustion, CO2, and then a portion, this is for a full fuel cycle emissions, so also including the upstream emissions from electricity and natural gas use, a portion from that as well, so about 2.6%. And when you put it in the context of an entire home, ends up being about 0.3% of the whole home's overall full fuel cycle CO2 equivalent emissions. And to put this in context though, it doesn't seem too big, but compared to the current emission factors that are being used, so say using the AP42 emission factor for enclosed combustion, then this would be 0.04% instead of the 2.6%. So a significant jump up from what might typically be used right now. This is just kind of putting this in context from the other 3 studies that I mentioned. This is steady state emissions, so kind of showing that there's good consistency between them. And then this just highlights again what I had mentioned before from, this is all Eric. But that emphasis on the number of activations per day for the tankless water heaters is really significant and is really going to be the driver of the emission rate that's assumed. And so for really for any inclusion of not just tankless water heaters, but other appliances as well, I think that we're going to be seeing a similar pattern. So inclusion of those, say, into inventories, getting a really good understanding of what a typical draw profile looks like, what a typical use case looks like, is really important for being more accurate in these emission rates. So what are we hoping to do next? One, understanding emissions from other types of residential equipment. So we're going to be getting some furnaces in the lab soon to do similar testing on those. And then along with that, I think really important for collaboration, both between research organizations like ours, academia, and also manufacturers, to work on development of standardized test methods as this starts getting more and more attention put on it. And then ultimately, as we start getting more pieces of equipment and measuring them, hoping to work with manufacturers on mitigation efforts.